So here we have a very basic kinematics problem. I'm making it as simple as possible, so I've done a couple of things. It's once again my underground cannon, so it's level with the ground. See that I have it at 0 for y, and I'm designating that as 0 in the x as well. It's firing something at a simple angle. Theta is 20 degrees, so it's a 20-degree angle at 30 meters per second. I am keeping my defined coordinates as up and down is y, up being positive, left and right is x, and to the right is positive. And it's on a very flat piece of ground. Then I have my question, where is it going to land? So I'm going to use my kinematics equations and some super common sense abilities to figure this out. Step 1. I'm going to label all of my variables for my x and y axis. Notice that I still use my standard 6 variables: velocity initial, velocity final, time, displacement initial, displacement final, and acceleration. I just have an extra designator for x and y, except for time, because we already said that time would be the same no matter what. Now let's do some super common sense to make sure that we can figure things out. So I'm going to go ahead and I'm going to start marking on here. I'm going to say that that's my halfway point, and I'm going to go ahead and mark it all the way down and say what I know. I know that t of 1/2 is going to equal t of the second half, since it's symmetrical. I'm going to say that at this height, my v in the y is going to be equal to 0 meters per second. I'm going to go ahead and say that it's on Earth, so the only acceleration I have is little g, which is equal to 9.8 meters per second squared. And that means that I have no acceleration in the x, so this gives me a whole bunch of different things I can go ahead and fill in on my chart here. So I can go back and I can say that this is 0 meters per second squared, which means I can ignore it. We already know that this is 0 meters. Let's do a better m. We know that, we don't know my initial velocity, but we know that my final velocity will be equal to my final velocity in the x. And then on my y side, I know that I'm starting at 0 meters again. I know my acceleration is negative 9.8 meters per second squared. I know my final velocity for what I'm going to look at is going to be 0 meters per second. And then I can then go about looking at this angle and initial velocity that it came out of the cannon with at 0 marker and break it down into its component parts. So let's set that up and do that. So I've set that up over here. If you remember, you just take your vector, such as this, with the degrees, and you break it down into an x component and a y component. Now I still use my same variables because this is an initial velocity, but I have certain amounts in the y and certain amount in the x. I use my basic trig function, so I'm using my hypotenuse, the vi, times sine of theta, my angle, in order to get what my VIY would be. And when I plug all of that in, I get that it's 10.26 meters per second. When I do it in the x, I do the same thing, and I get that it's 28, I just have to use cosine for that because it's adjacent, and I get 28.19 meters per second. And so that would be my second value. I now have 2 more things I can add to my overall sheet, so let's go back and add them there. So now that I've put those values in for my velocities, notice I didn't need to rewrite it for this because we know that these are going to stay the same velocity in my x. I now have both of my equations down to only 2 unknown variables. The only thing is, really, in order to have this one for 0 meters per second, I need to make a small adjustment to where I actually say this is time to 1/2. But because of down here, we said this is t of 1/2 equals t of 1/2, we can just double it in the end to get this time. Okay? Now, the other super common sense thing you need to say is, well, if this is a velocity with no acceleration and there's no wall here, then if it was just going in the x direction, it would carry on forever. It would not be limited by my x. But because this has an acceleration, a negative one that is even opposite of its velocity, it's going to go up a certain amount and then down a certain amount, and the ground will stop it. So y is our limiting factor, and we have far more formulas to fit y than we do x, because x is a constant velocity and y is a constant acceleration. Then we have our 4 kinematics equations for constant acceleration for y, but only the one for our constant velocity. And since we only have one equation, it has 2 variables. We need to figure one of these out first before we can do that. The only thing that they have shared is time. So let's try to figure out time in the y-axis. And to do that, I'm going to look at my kinematics equations. Now, because I'm missing 2 variables, a time and a displacement, I need to find one of my equations that doesn't have that. But remember, our overall goal is to find the time. So I'm probably not going to use the one that doesn't have time. I'm going to use the one that doesn't have my final displacement. This first equation right here, it has a final velocity, which I have, initial velocity, which I have, an acceleration, which I have, and a time, which I can solve for. So let me use this one to figure out the time. And remember, it's a half time for this overall equation. So here, notice I've written down my equation and I've made it fit the y-axis that I have. So my VFY is equal to my VIY plus my AY times time 1/2. I even put my designator for my time. I just used my simple algebra here where I did subtracted VIY from both sides, cancels on that one, get a whole new equation, then I divide by AY, cancels out on that side, and I get my final equation where I can now feel comfortable plugging values into it. I really want to start working it out before you plug the values into it. It shouldn't matter too much, but it tends to help keep your math honest and right. A lot of you are screwing up with the algebra. Okay, so once I have that, I can put that we have 0 meters per second minus 10.26 meters per second divided by a negative 9.8 meters per second squared. And I'm going to get a t of 1/2, which is equal to 1.05 seconds. And I'm going to instantly multiply it by 2 so I can get my full value. And I get that t is equal to roughly around 2.1 seconds. You might round slightly different, but it's okay. This is the actual value I want because I wanted t, not just t-half. And I wanted that so that I could plug it into my x value, okay? Because it's our x which will determine how far it actually goes. Also, part of that dimensional analysis, let's use blue for this. If you look at my dimensions here, meters per second minus meters per second divided by meters per second squared. Well, you can subtract and add only like units. So meters per second to meters second equals meters per second. But I'm going to get meters per second divided by meters per second squared. And dividing by a fraction is the same thing as flipping and multiplying. So let's do that. I'll flip, multiply. Now I have seconds squared over meters. And notice with that, my meters would cancel out, and the seconds on bottom would cancel out just the squared, so I would end up with just seconds. So I know this is going to give me a right value. It's one of those dimensional analysis things that helps. Okay, now that I have my time, I plug it into my x-axis values, and I have everything I need to solve for my final one, except for, if you're forgetting, the equation that we actually need for constant velocity. And that's simply df is equal to di plus velocity times time, okay? So as you can see, we have all the variables that we need. We only have one velocity because we said there's no acceleration, and we have our initial placement and we have time, so we can figure out where it will land. Let's do that real quick. Notice I set up that one equation that I have for my x. I go ahead and plug in my values because it's already solved for df final x. And I'm going to get, and you can get, depending on how you vary, you rounded anywhere from 59.03 meters to 59.2 meters. And so that would be our answer of how far away it landed. And that's all there is to it.